Yeah. Present your screen. You can share your screen and
Yeah.
start the system. Yes.
So yeah, hello everyone again, and yeah, let me share my screen. Mm, Right. Okay. I hope everything is visible. So yes, so let's start the hands-on session. So if I have to quickly recap what we discussed in the last, let's say, tutorial, is that okay? We started something with the transformer model, and then because transformer model is the part of the every foundation model these days. So with the transformer model, we moved on to the masked autoencoder, then to the vision language model like clip, and then on the SAM. And then how to we have this question how to adapt this SAM model for the medical image segmentation, right? So then we see our method, the SAM member, right? So the hands-on session also we follow this kind of the flow. We start with something with the transformer model, how this self-attention, this that it works, and then we go to this mask autoencoder, and we take the flow from there, right? So with the transformer, so what I would try to do is I'll try to click on these the collab links, and I'll try to execute the and discuss how these executions are being done. And maybe if it is possible, can I share the slides with you if you want to run it by yourself on your collab? Is it possible, sir? Or I just execute by myself?
Yeah, you can just now execute and
All
display
right.
them. Later we can and they
Okay.
can
Okay.
there also I think you can just directly interact with them. They're also okay.
All right. Okay. Okay. Okay, so let's see how this self-attention works, because self-attention is the building block of the transformer network, right? So let's go this to this link.
So either you can show them or they later you can share the link with them. They can practice, right?
Okay, I put the link on the chat box. So the first one, let's say the
Yeah, yeah.
self-attention.
Put over there.
Or,
There is
or maybe it's better I saw that and
comment
then
box
I
also you can
share the
check.
slide.
The comment box also you can check.
Comment box.
The
Okay.
things okay, they are writing yes. Today's session has delayed. No, no. The last session actually was about to start at 7:30. So it started on 7:35. We're only 5 minutes late. Yeah.
Okay, so let's start with the self-attention, and for the convenience, I'll share the slide entirely at the end. So, it will not break the flow. So in the self-attention, what we have is, if we recall it correctly, we have the key query value projection, and the key query, then we multiply the key query to generate a attention map, and then we the softmax activated attention map we multiply with the value to get the final enhanced feature, right? So if we say that, let's say we have three inputs, and that is going to this key value projection. And then let's say the third input is the query. The first two input is the key value, then it's a query, and you're trying to multiply. And there is this output. Okay, these are so fast, it's hard to interpret. All right. So, okay, let's assume that we have this input, X is the tensor, three inputs, and this is float 32. And we want the three projection, that is the key query and value. For that, we define, let's say we initialize three weight matrices: weight matrix for key, weight matrix for query, weight for value. And by multiplying these three vectors, input 1, input 2, input 3, with these three metrics, we can obtain, let's say, the key is like this. The values with the value matrix, when you multiply, sorry, key query value, right? So the key, when you multiply with this one of the key matrix, you get the key, right? Then multiplying with the value matrix, you get the value vectors, and multiplying with the query matrix, you get the query vectors. Okay, so we have three uh, feature maps right now: key, query, and value, by with some initialization. Usually this is random initialized, but for convenient, we say this is three different binary metrics as weights. So this is done by simply like X multiply with weight of key, the input multiply with query, weight of query, input multiply with value. So you get three values, right? After these three values are multiplied, in order to obtain the attention score, first we need to multiply the query and key transpose, because we want n by n matrix. So because this is a matrix multiplication, not pointwise multiplication, so one has to take care about the dimensional matching, right? So the attention score is multiplied by query into key transpose, the transpose of the matrix. So this is the attention metric. So this is the score. Now one has to activate with the softmax activation. Okay. So from torch.nn, we import the softmax activation, and we apply it with the softmax with the attention score. So now we can see that all the values in the attention score is the sum total is so this is across one input. So for this matrix, for this vector, the sum total is 1. This vector, this sum total is 1. Here also the sum total is 1. So in the vector 1, the values at index 2 and 3 is more relevant. In the vector 2, the value at index 2 is important because it is the highest attention score. And here it is the index at 2 and 3. Right, 2 at least. And now the idea is to, as this is the saliency map for the entire input map, the idea is to multiply this attention score, that is softmax activated, to to the values, right? To the value feature, value vector. So once this is multiplied, so this is the entire outcome. So out of the three input, if you say that in the value, the sequence at the second sequence and the third sequence had some relevance, and the first sequence is kind of non-essential for the task, let's say. So if you have this, so this is the weighted value, right? Okay, so below there is a TensorFlow version, but TensorFlow version, I won't go in detail, but if I have to go slightly, that okay, first this is the input, three weight matrix. So here with the TensorFlow.matmul, you can do this matrix multiplication of input to the weight. And for attention score also, you need to do the TF dot matrix multiplication between the query and keys with transposition as true. And then softmax activation. So instead of torch.nn, this is tensorflow.nn. And after the softmax is activated, then you kind of multiply the value with the softmax activated one. And then at the end, you have the final uh, attention modulated feature input map. Okay. So I think this part is simple and clear. Then we can go to the next part. If you have some question, there is questions. No. All right. So the next part is the position embedding, or do we have time, or we will only focus on the crucial part? Okay, let's go to the transformer with the for the text task. So position embedding is just adding position information to the one. So let's go to the transformer. If I have to, if we have time, we go there. I mean, so for the transformer, what we have is this is a typical transformer. So first you have this input with the embedding with position encoded embedding, and then it goes to this transformer block, right? So okay, so if I have to define a transformer model, so there is this. Okay, so there is this encoding layer in the, so I have to define a class, and inside the class I have this position encoding one as a function, and encoder layer is the transformer encoder layer, or let's say the self transformer encoder is the transformer encoder layer that takes how many encoding layer we want, and how many layers. Okay, so first what it takes. Okay. Okay. So it takes a sequence in the forward function. If we see that it takes a sequence, and this sequence is position encoded. And once this is position encoded, this is given to the transformer encoder. Okay. And with a mask. So if we want to access to the future sequence or not, if it is a causal, then the mask is in a triangular shape. You only have access to the current sequences, not to the future. But if it is a causal, you have the access to the both past, current, and future, right? So okay, if I have to show this input. So here as the input of the transformer model is the text. So it takes some text data. This loads the data set, and from this data set, this is the wiki text2 data set, and it splits into train, validation, and test. From the train set, it kind of do the batch, because we need to do the mini batch training with a batch size of 20. So it also do the batch for train data, validation, and test. So when it is a transformer model, we cannot load the entire data set to the GPU. It will overflow the GPU memory. So this is a get batch function. So for you pass the data loader and with the index, so it will generate a batch of batch size, let's say 35. And then you define the transformer model here. And in the train function, you load the text tokens. So these are the end tokens. And okay, but where is this transformer model? Okay. Okay, so it takes that transformer encoder from the inbuilt function of the torch.nn. So if we see the transformer encoder is taken from the built-in function, or one can define by themselves, but this is the highly optimized function to call. So it is taken from here, and then it trains the network by loading the batch. It enumerates the batch, and for each batch there is the data and target. It feed it to the model with the output. It applies a criterion function, and it does the backpropagation. After end of some iteration, it does the evaluation. Okay, and this is a I mean similar to the any of the network training reason. So you train the network after each epoch. You see the how much time does it take and what is the validation loss, kind of thing. So I hope this part is not that difficult to understand. Okay, so once we have this, so as we have seen that the most of the model, the transformer, the crucial part is taken from the built-in function of torch NM. So this is also part of any for true for any other foundation model, right? So if I have to go next, we can directly jump into the MAE. So in the MAE, what we have seen that this is also the vision transformer. Uh, the only difference is the encoder is a huge model vision transformer, and decoder is a smaller model. So there is asymmetricity. But the key things lie over here, other than the data set curation and training recipe. The key thing is how to do this kind of masking. So let's see this kind of in a collab. So in the ME, okay, do I have any questions? No. So okay, so installing few packages, and okay, this is a package installation. So here there are three main function to see a image. For example, the image you load, you see, and then preparing the model that we want to. So this is the MAE bit large with a patch size of 16 by 16. Right. So we take this model, we load the checkpoints, and okay, for the you can choose the resource either as CPU or GPU, but let's say just for one run, CPU is enough, let's say, and then you load the model state dictionaries, the checkpoints, and other parameters. And this is the function to run on one image. So you take the image and you take the model, and then this model will run it. So we'll come to this slightly later. So let's say we load an image, that is image from a particular URL. You do some resizing and normalizing. So this is the image, okay? And then we load the MAE pre-trained model, that is the MAE for visualization, the large model. And then after this checkpoint, we pass it to the prepare model function. So this is the prepare model that takes the checkpoint directly. And here it calls the get attribute, right? And then once the prepare model will return you the model with the checkpoint loaded to the model. Okay, so this is ready to use the model underscore ME. This variable is this object is ready to use. And then as we have the image, so we take the image and we take the model, the ready to use model, and we pass it to the run on one image. So this is the image we pass. So let's see what it does. So it takes the loads the image to a tensor. Okay, and okay, this is the part of the model. Uh, so it takes the model. So X is the image, Y is okay, and then it gives the X to the model with a mask ratio 0.75. So it is the 75% of mask ratio. Okay, and it obtains two tensor, that is the Y and the mask. Okay, and with the Y and so it tries to unpatchify and okay, and the mask. So it returns output image and the mask, right? So it is kind of squeezing and unpatchify this, and it as it was running on GPU, it tries to detach and make it to the CPU, and then it multiplies the input image. X is the input tensor with the mask, one minus mask, and this is the this will result in the masked image, and then masked image plus the reconstructed mask. Okay, so we have two resultant output, that is the image with masked and image that has the addition of this the prediction mask. Okay, so if we see that, so this is the original image. We do the masking with 75%. So this is the mask returned by the model. And when you reconstruct, so this is the Y variable or the Y tensor with the reconstruction. And if you want to add the reconstruction with the original, so then it is the more smooth part of the image. So it means that the model which is pre-trained on with this checkpoint, if you pass this original image with this amount of masking, still it is able to reconstruct this kind of image, right? So okay, so this is with okay, so this is the part with the reconstruction loss. So the MAE can be trained with two kinds of loss function. One with the mean squared error, the reconstruction loss, and it is also possible to have with the GAN loss function. So if you load the checkpoints of the GAN loss function, so we can see that the reconstructions are more appropriate and more fine. The fine details are preserved in the reconstruction. But with the simple reconstruction loss, there is some um, this kind of pixel effect, so which is not that smooth. Or if with the model with the GAN loss, it has the more fine details information in the reconstruction. So okay, so I'll share you the this thing. So I let you run by on your Colab profile. Then we can go to after the ME, we can go to the, so okay, so this repository that I'm trying to show here, these are the quite basic one, and to visualize the functionalities of these models, but there exist many repositories in the web that can give additional more functionality on the this kind of models, right? So then we can go to this clip. Okay, so in the clip, if we remember correctly, that so this is a visual language model. So the first one, it is a reconstruction or generative based self-supervised model that tries to generate something in the encoder decoder structure. But the clip is it's a contrastive based foundation model. So it tries to learn the similarity between the image and text pair. So that's why it has two encoder, image and text encoder, and it tries to learn this kind of similarities. So we'll see the key part over here is the image encoder is the weight one. So we have understood this part already. So the key part is how this similarity is being computed or being learned. We'll see in this in this session right now. Okay, so this is a quite well established repository. So everyone can use this part. So let's say these are all installation in the beginning. Okay, we clone this OpenAI clip repository. We add the plugins and okay. So where do we load the data set? Mm, okay, so this part is commented. So this part it loads the data set. So okay, these are the data set. Uh, okay, from the data set, it took the test part and the tokenization of the text. Okay, so in the test set, it has three classes, for example, and it takes all the images from the test set and in the tokenization text. So it has all these class name, let's say scissor, rock, and paper. And then, okay, here is the crucial part, I would say. Here we load the model, the clip dot load, and this is the, as we know, the image encoder is the bit one, and this is the model and the model specific transformation. And from the clip, we also load the text encoder. So this model is the image encoder, and this is the text. And there, what we do is from the data set location, the test part, we load the images, that is the test images. So we load all the images. And then for each image, we apply the image transformation corresponding to this vid model, right? And then from the model, we encode the image with the image we load from this test set for the, let's say, the first image. And we have the text part from coming from the tokenization of the clip model. Okay, so this is the one image with all the text features, right? And once we have these two features, the image features and the text features, we pass it to the model, that is image. Okay, so these are the two features. If we want to, for example, like these vectors, this the I1 to IN and T1 to TN. But if we want to directly compute the similarity between these two, so you directly pass the image and text to the model, and you get the logits per image. So these are the logits per image and logits per text, and you apply a softmax to see the probabilities. Okay, and to those classes you have the highest probability. You say that this is the prediction from the class name, right? And there you can see that, okay, the accuracy on the class of Caesar. So this is all zero shot. So if you can see, this is torch with no grad. So there is no gradient is back propagated. With zero shot for the Caesar class, there is 54% accuracy. For the rock, 8, and for some classes, this is 0 because of the, let's say, domain gap. So, but for overall, this is 24%. So it is on a test small data set. So if you want to try the zero shot on your data set, so these functions can be adapted, right? Okay, so then I think for the segmentation, the one of the major part is the SAM model. So if I have to quickly recap the SAM model. So across all these three foundation model, the encoder is always the bit. So image encoder is the bit, in the clip in the image is the bit. Similarly, in the SAM as well, the image encoder is the bit, right? So from the image encoder, you get some embeddings, and then we try to prompt with the mask decoder, and we get it. They'll get the mask. So let's see. And from here, we go to the SAM Mamba right after this. Okay. So we follow the same setting, and okay. So we clone the SAM2 model, bunch of installation. Okay, we load the images for a dog image. Okay, from this example, key in the packages. Okay, we read the image right here. Okay, so let's see. Okay, mask generate. So here we call the SAM automatic mask generator model with the SAM2. So the object is the mask generator. And once you load the image, this is the image RGB. So mask generator dot generate. So this is the generate function, and if you pass the image as input, it will show you the give you the result of SAM2 dot result. Okay. So if we try to visualize the SAM2 result, so mask generator SAM2 result. So so this function visualizes the SAM2 output. So this is the image, and if we see, this is the segmented. So this is the panoptic segmentation. So the segmentation of the sky, segmentation of the building, segmentation of the dog, the tie, the cap, I mean everything, the bags, everything. So this is the all object, like the panoptic object segmentation is right here. So if we want to visualize the mask individually for each kind of object, so one has to iterate over the mask from the segmentation. And then you can see that the mask for the dog, this and that, these are quite crisp. The mask for the sky. So it shows that the segmentation is quite effective. Okay. So if we see that, if we try to change some of the hyperparameters, like if we change the IOU threshold and other threshold, then the mask generation is even more accurate, because in the first attempt, the segmentation of the t-shirt, this human is missing, but by changing the IOU threshold, the segmentation can be enhanced. So yeah, so these are the part of the hyperparameter tuning during the um, zero shot evaluation. So I think this is also for image when you pass the bounding box as the prompt. So if you pass the bounding box as the prompt, so you try to encode it here. And then in the predictor function, you give the box as the boxes, and you get the mask, score, and logits for 3. Okay, so for these 3 bounding box that is provided as a prompt to the decoder, so only those 3 objects are being segmented, right? So prompting with points. So if you want to give a points, for example, for the human, for the hand, for the t-shirt. So if you give the points as this, so these are the 3 different masks for the 3 different points, right? Okay, so this is the SAM part, and as of now, what we have seen is how these foundation models are working in the real world, or on the general object segmentation or classification. But the question is, how can we adapt this SAM model to the medical image segmentation? So that's why I'm gonna present our the SAM Mamba next. And we saw that, okay, I need to open the slides of SAM Mamba, right? So yeah. So in the SAM Mamba, if we remember correctly, there is there is this SAM encoder and SAM decoder. On top of that, we have this Mamba prior module, and there is a adapter network on parallel with the SAM encoder that iteratively take information from the SAM encoder and inject it to the each layer of the wheat block, right? So if I have to show that in this, how this function is being defined. Okay, so here is the package for the Mamba SSM. We install that and okay, so these are a bunch of activation functions that is defined for, I mean, every project. Okay, so here is the class for the SAM vision. Give me, yeah, so this is the SAM vision attention module here. If we see that the attention modules are, okay, this is a more matured implementation. This is right. Okay, so this code repository is being developed by the first author. So first author. So we have taken it and we're trying to understand what he has done. Okay, so this is the self-attention and part. Same vision layer. There is a custom network somewhere. Hmm. Okay, so this is the custom network. Yes. So if we have to see this code and along with this model, so the image, it goes to the patch encoder, and this is the regular wheat encoder of the SAM. And the same image also, it goes to a Mamba prior module along with to the adapter network, right? So let's understand how this model is being defined. And this Mamba prior module, it goes to the feature pyramid. It has this multi-scale feature decomposition with different convolution filters. And then there is this stacking is being done with pooling. And then there is this Mamba for fixed order feature pyramid relation encoding, right? So in the custom model, if we see that this L1, L2, L3 corresponds to the three levels of decomposition with kernel size 3, 5, and 7, right? And there is this, the saliency pool corresponds to the max pool, the context pool corresponds to this average pool, right? And then this is this Mamba block that has, we want to keep it lightweight because the, as I say, there has to be a trade-off between the model parameters and the amount of data we have, data sample for the training. So in this case, we have less amount of data, so we try to keep it as light as possible. So just to one model with one state space. So when we have the input X, so this is the image. It goes to three level of decomposition that gives you out one, out two, out three. And then this is concatenated or stacked across the batch dimension. All right. And then this is passed to the another convolutional layer for feature mixing. And this, the output of this convolutional layer is first average pool and max pool on parallel. And this average pool and this one are given to, okay, so this is the part where it is commented. So it goes to the Mamba 2D block, the concatenation one, and the final outputs are multiplied with the output of the Mamba. This is the out LSTM, let's say, and then it is multiplied and it is returned to the. So this feature map is the output final, right? Okay, so and as this model has to be repeated for n blocks of the V transformer, so we are applying it to each layer. So this is being repeated for each of the blocks, let's say block 1, block 2, block 3, with different input feature dimension, right? And this is the final model. So in the weight adapter, we call this the weight adapter, we call this repeat custom model. So this is the weight adapter. We call this repeat custom model, and then uh, this model is being plugged into the weight transformer, right? So soon we're gonna release this kind of this code on the public domain after maybe cleaning some of the things. And yeah, so okay, does he have the output? Let's check the output. Okay, so these are the images he has in the pixel in the mask, the ground truth mask. Okay, this is all right. So the crucial part is on the model, how we define this kind of the Mamba prior book. And yeah, okay, maybe I need to see if we have some questions. Okay, so probably this would be the end of this session. Maybe if you have some question, uh, I'll be happy to answer. To stop sharing. So yes, if you have some questions, you can post, or maybe then we can discuss.
Yeah, participants, if you are having any queries or I'm in the course, do you need codes actually? If you need codes, then provide the link.
Yeah. So I'll share the entire slide.
Yeah, that can be shared with them.
Yeah.
Yeah, there is a question, please.
Laptop configuration that would support. So the execution of this kind of codes is on the cloud, so on the Google Colab. So or paid version would be sufficient. So maybe you may not need the paid version for the basic experiment, but if you want to train a model, yes, you need a paid version on the Colab. Okay. Any more question? Yeah. All right. I think this
Yeah, how can, yeah, there's another question. How can this person, okay, these region foundation models help in classification task?
So yeah, I think these foundation models can help in any kind of task. So maybe it is a segmentation, classification, or anything. So in any machine learning or deep learning pipeline, wherever we have a feature extractor, wherever we have a need for feature extractor for image or for an input image or video, this foundation model can act as a feature extractor that can give you pretty good quality features. Uh, and then you can adapt into smaller network with a classifier with other functional module, right? But the foundation model can definitely give you good quality feature uh, for uh, for many tasks. But if the task is if there is a high domain gap between the pre-trained information of the model and the target domain, then you need to apply some sort of adapter, right? Even for the classification task. So yeah, I think this answered the question.
So any other questions from the participant side?
Okay, so we can end the session.
Yeah,
Or
I couldn't find any